like we've got maximal attendance for a 6 p.m. math class now.
Yeah.
Really off to a good start. Okay, so I don't really have any particular announcements. The quiz was due on Saturday night, but I think most people submitted when I just kind of glanced over it. I haven't really started grading yet. I plan to do that probably today or tomorrow. My goal is to always have it back to you for Wednesday before the next one, just in case there's something that we needed from this one that you want to know for the next one. It's like, well, if you don't have feedback for that, it's like you're still sitting there going, but do I understand it? So the goal is to get it back to you by Wednesday, and that works out for my schedule too. But otherwise, I don't really have anything specific to announce regarding that. So I guess we'll just jump straight into it. So last class, we talked about truth tables and how to build them. Just a bunch of examples, and then we did the quiz on it. I also, at the end, talked about this idea of a tautology, which I sort of implied we want to treat it like equality, right? It's the logical version of equals, right? These two things are the same, so we can replace them with each other. That's the goal there. But something is a tautology if you build the truth table and the final column all t's. It's just always a true statement, no matter what your inputs are, right? You can put in anything you want, it will spit out a true statement. So we're just going to write down a huge list of them, and it's not even complete. There's some I'm not going to write down that are on this list, and there's some that are just not on this list because I just didn't include them. And this pen is terrible. Well, I don't know if I can make that garbage can, so I won't try. There are people over there, and I don't want to hit you with a marker. Although, if the marker ended up over there, then I'm like way off. That's like an embarrassment. So the following are tautologies, which ultimately means we can replace one with the other. So we did this one. So the important thing here is this symbol in a tautology means you can swap one with the other. So like if you see this written down, you can replace it with that instead, anywhere, right? Because they're equivalent to each other. So this is called double negation. And now we're going to write down some that are, they will seem kind of familiar, and that's not really a coincidence. So P or Q is the same thing as Q or P. And that kind of makes sense, right? We just think of like a truth table. It like doesn't matter which order you write them down in your truth table. So obviously this is going to be the same. Similar thing holds for and. Q and P. And because in math and logic, we have to have a big fancy word for literally everything. This is called the commutative law, which you've seen before. Maybe you just don't call it that. Like we look at this is saying P or Q is the same thing as Q or P, right? Essentially, we can do that order interchangeably, right? Where else have we seen that? When you add two numbers, it doesn't matter what order you do them in, right? 2 plus 5 is the same thing as 5 plus 2. Doesn't matter. Another one is what's called the associative law. I'll first here. So we have these brackets here, right? P or, and then in brackets Q or R. So what this is saying is it doesn't matter what order you do your brackets in for this specifically. And same thing for and. So you can do your brackets in either order, which in practice means we just don't write them, right? Like think in terms of numbers. Again, x plus y plus z with brackets is the same thing as x plus y plus z. But with numbers, we just wouldn't even write the brackets at all, right? We would just not do that. So this is called the associative law. Now, with these two, specifically, they're kind of interesting in the sense that you look at them and you're like, yeah, aren't those obvious though? Like, obviously that's true. My answer to that is no, it isn't obvious. These aren't things we can take for granted. This one here, associative law, I would say is like 95% of the time true. Like if you think of some operation, so like, you know, yeah, we've got this or, we've got this and, we've got addition, we've got multiplication, that sort of stuff. Just any operation like that that you can do on numbers or something, this is probably going to be true. Or objects, right? There are situations where it's not. They're really weird though and specific. This one though, we can't take for granted. This actually ends up being not true relatively often. So this idea that you can sort of swap the order of this fails quite often. And we're even going to explore that in this class. So if you know it, matrix multiplication is not commutative. A times B is not the same thing as B times A in general for matrices. So my point here is you see me writing these and you're like, yeah, obviously those are true. Why are you even writing them? Because they're not always true, right? We take them for granted. Okay, so the important thing here, though, and students very frequently get this mixed up, these are the same. They're the same operator, right? And here we have or, right? They're the same. Because students often mix it up with distributive, which is P or Q and R. So you see, these are different now inside the brackets. These are different rules. P or Q and P or R. So these are different. So that should be your Q. If they're different, I use this rule. If they're the same, you use this rule, right? Again, oftentimes this rule is not super important other than like academic exercises that I'm going to make you do, where I have these brackets written down, and really it's just to get you to mix these up more than anything. But this is an important rule. P and Q or R. So this is P and Q or P and R. So this matches a sort of familiar rule in math. It distributes, right? This thing sort of goes over the brackets. So this is the distributive law. And again, it has a mathematical equivalent that you've seen before, just like these two. If you've got x times y plus z, well, this distributes over the brackets. You've got x times y plus x times z, right? Just with numbers, right? So this is also a familiar one. But now we have some unfamiliar ones. So an example, and these are more proof-oriented. They're not really corresponding to math operations with addition. So P implies Q is the same thing as not Q implies not P. And this is actually a really useful proof technique called contrapositive. Again, I have spared you from proof techniques. I'm axing that topic. But it still comes up relatively often. So this is saying if something, then something else. What this is saying, if not something else, then not the original thing. Right? So if you build the truth tables for these things, you'll see they're the same, which just means sometimes arguing this way is very hard. Like if this is true, then something follows. But then you flip it, you argue like this, and then it becomes really easy, right? When you sort of argue in an opposite manner, right? We also have these, the absorption laws. And again, this is important. These are different symbols. P and P for Q. So again, different. My red pen is dying. So these are different symbols. So what are these equivalent to? Well, good news. Just P. Right, so what this is saying is if you've got something that looks like this with different symbols, this P here absorbs that stuff. It just goes away, right? It just gets kind of sucked into P and you just don't care about it anymore. Okay, so far though, what it looks like we've got, and the reason why I was writing these down, like this one here, also, is these logic rules correspond to algebra rules, right? Which means we can do some form of algebra with this logic stuff. And you might think, okay, well, why am I looking for excuses to do algebra? Ultimately, it's because sometimes you'll have really complex logical statements, and if you can do these sorts of rules, you can simplify it. Again, leading statement, what does simplify mean? In this case, it's pretty obvious. You have a big, long statement. A really small one is simpler, right, in this case, because if you're trying to build a truth table, you've already seen that the more pieces you have, the longer your truth table is. So if you can condense that, it's easier to build a truth table. And also, it's just easier to, sort of internalize what is being said when you have a simpler statement, right? Like in terms of English or in terms of programming logic, right? If it's the simpler it is, the shorter it is, the easier it is to sort of understand what's going on, right? So we also have two more. Again, no corresponding math rules here, but they can be really useful. P or not P. So let's think about that. What could we replace P or not P with? Let's just think, what would be the truth value of this thing? So if P is true, what's the truth value of this statement?
True.
And if P is false, what's the truth value of that statement?
True.
Yeah. So if P is false, then not P is true, so the whole statement is true. So that means regardless of what P is, we can write down T. And we just write down it's true, right? And that can be helpful because if you have, these are just thinking logically, like if you have P and T, well, this is the same thing as P, right? Because it doesn't matter, right? The fact that this is T just means this is always going to depend on what P is, right? So you can simplify things, right? If you have this, it goes to this, and then it simplifies further, right? So you can see how this removes pieces of the puzzle. Similarly, P and not P, what's that going to be? Yeah, right? Same exact argument. If P is true, then not P is false, so this whole thing is false. If P is false, then not P is true, but P is false, so the whole thing is false. So we can replace that with false. And again, where would we care about that? Well, P or F, it's the same thing as P, right? It only depends on the value of P, because it's just something false, or P, which is just P. So again, useful for just sort of condensing statements. So the point is, this gives us some algebra rules. Which is great, because it just means we can simplify things. That's all algebra is, right? I mean, that's a fleeting statement, right? When I boil it down like that. But the reason we care about algebra is to just make things easier in theory, right? If we've got some big, messy, ugly thing, then we have a prescribed set of rules that we can use to make it smaller or easier to read. Okay, so there is one thing worth worrying about. So we have the distributive law here, which tells us how and interacts with or. But what about negation with either of those symbols? So what I mean is, how does this work, right? I mean, we think this happens all the time in math, right? Negative of x plus y. That makes sense. We would just go negative x minus y, right? So how do we do that here? Well, it's almost exactly what we would think. So we're going to spend a bit more time talking about this. So the naive thing or intuitive thing is to say, well, is that, right? But if we actually write down the truth tables and whatnot, that doesn't work out. It ends up flipping the sign here, right? The or becomes an and, or the and becomes an or. So this is called De Morgan's laws, which we're going to talk about. But before we get there, there's something else I have to talk about, because there's two forms of De Morgan's laws, and one of them uses the next thing I'm going to talk about, which is quantifiers. So a lot of this logic stuff is just a very formal look at what ultimately is just plain English, right? It's stuff that, it's how we talk, right? These are all phrases we say. So quantifiers are very similar. And they're always there. Like, honestly, most of the stuff that you've seen, they're there. We just don't write them. So recall, a formula depends on the values of the variables. So what I mean by that is the truth value. So something like and x bigger than 3. So it says x less than or equal to 5 and x bigger than 3. Okay, well, if x equals 4, is this true or false? Yeah, right? 4 is less than or equal to 5, and 4 is bigger than 3. Okay, well, shocker. X equals 6, true or false? Yeah, it's false. Because x is bigger, or 6 is bigger than 5. Okay, so yeah, we could choose values of x here to determine whether or not it's a true or false statement. So compare with the following statement. For every x, so we've sort of added this quantifier here, right? We've, instead of just blah, I've said, hey, for every x, x is less than or equal to 5 and x is bigger than 5. Is that a true statement or a false statement? Yeah, right? Because what I'm saying here is, for every possible choice of x you could make, x is less than or equal to 5. Well, no, 6 is bigger than 5, right? So, no, this is false, right? This can't be true. False. 6 is bigger than 5. Right? So that automatically makes that false. But what about this too? So this is 1. There is an x such that, same thing. So this is saying, hey, there is an x so that x is less than or equal to 5 and x is bigger than, or that should be 3. Is that true or false? Right, yeah, because 4, right? I pick 4, that's an x where this is true, right? But see, the thing here is this way of writing the statement depends on your choice of x, right? For whether or not this is true or false. If I said, hey, is this true or false? You'd be like, I don't know, what's x? Here, though, it didn't matter what x is anymore, right? This is a blanket false statement, and this is a blanket true statement. So these lines here, the for every x, and there is an x such that, changed this, right? We no longer need a value of x. We actually get a definitively true or false statement now. So these are quantifiers. So the phrase for every x, or for all x, or there's lots of different ways to say this, right? It's just saying, hey, for every possible choice, right? No matter what you pick, this is true. Is called the universal quantifier, which makes sense. It's saying, hey, for everything, right? Universal. It for everything. And is denoted, it's an upside down A, right? Just to make it clear, like distinct from an actual A, right? This is a symbol that says for all. The phrase, which is a bit of a mouthful, there are lots of ways to phrase this, but there is an x such that ... or I can find an x exists such that, like there's lots of different ways to say this, is called the existential quantifier. And not like an existential crisis like a math class or something like that. I make that joke every term, no one laughs. So that's why I continue to make it. Maybe someday someone will laugh. So this is denoted by, well, we use an upside down A for all. So what do we use for existential? Upside down E? No, we use a backwards E. Because an upside down E is the same as a regular E. So I guess, you try one thing. I probably, when someone was making these symbols, they wrote down the upside down A, and then they actually probably wrote down an upside down E, and then they were like, wait a minute, that doesn't work. And so then they just flipped it. So these are useful because they take these statements with formulas and turn them into things that have definite truth values, right? Instead of depending on a choice of x, they now just have specific defined truth values. So let's just talk about these in a bit more detail with some examples. And again, the real reason we care about these is twofold. One, they're always there. We just don't write them. And so understanding which one is being used is kind of important. But also, too, De Morgan's laws uses these, so we need to talk about them for that. So the sentence for all of x, p of x, is true if and only if, which is fancy math words for that symbol. So these are the same things, right? This thing being true is the same as for all possible choices of x, P of x is true. So that's a pretty strong statement, right? To say that for every possible choice. Because just think of this. If we were saying that for numbers, well, how many numbers are there? Yeah, a lot, right? In fact, depending on the context, there are infinite integers. There are also infinite real numbers. There is an order of magnitude more real numbers than there are integers. In fact, we have a special name for the amount of real numbers, and I love saying it. It's such a fun thing. It makes me sound like such a nerd. It's the cardinality of the continuum. That's how many real numbers there are. Just a lot, like an insurmountable number of them. So if we're saying, hey, it's true for all possible x, that's a lot of choices for numbers, right? That's a pretty strong statement to say it's going to work no matter which number you pick. So, some examples. So something like this. So let's try to decipher what these symbols actually mean. Like, what are we actually saying with this? So, well, first of all, I mean, even looking at it, does it look like a true statement or a false statement? So people say true. So let's try to think about what this is saying, right? So this is saying, for all choices of x, x squared is bigger than or equal to 0. So now, devoid of the symbols, does that seem like a true statement or a false statement? Right. And barring complex numbers, because I squared is -1, don't worry about that. Most people will look at this and they'll think, yeah, just numbers, right? Like integers, real numbers, that sort of thing. And for that, yeah, this is true. For all possible choices of x, x squared is bigger than or equal to 0. Okay, what about this one? Does it look true or false? Yeah, so this is actually something we already had written down. This is the commutative law for addition. But let's just try to unpack this, right? So this symbol just means for all choices of x, or for every x, or whatever you want to say. So for every x and for every y, right? Because these are independent from each other, right? You can pick an x and you can pick a y. It better work for regardless of what you pick, right? Now you have two choices, and it doesn't matter. X plus y is the same as y plus x, which this is true, right? This is the commutative law for addition. We know that's true. 2 plus 5 is the same thing as 5 plus 2, right? So this quantifier here shows up in a couple of places. The most common is just sort of in mathematical statements, or proofs or something like that, or theorems. So this often appears in theorems or formulas. But we usually don't write it, right? So just think of every formula you've ever seen written down, right? It doesn't say for all x, blah, right? It's just the formula. Because we just sort of implicitly assume this is there, because if you have a formula written down, you kind of assume that it's true for all choices, right? Otherwise, what's the point? Why would you have a formula that's only true like half the time? Unless it's indicated, right? It would say like true for x bigger than or equal to 0 or something like that, right? We would add some extra quantifiers there. But if it's not written there, we just assume it's true all the time, right? So even though we don't write it, it is always there. So let's try going the other way, though. right? Here, we went from symbols to words. Let's go from words to symbols. Let's consider if x is negative, then so is its cube. Right? So this is something we know to be true, right? If you take a number and cube it, if it's positive, it stays positive. If it's negative, it stays negative, right? -2 cubed is -8, right? So it keeps the sign. That's all this is saying. So let's try to put this into symbols. So this means, really, we don't write this. This is how we would write it in plain English, right? If x is negative, then so is its cube, or so is x cubed. But what this really means is for every x where x is negative, then x cubed is also negative, right? So we don't write this usually, but it is there. So in terms of symbols then, so for all x, where x is less than 0, that means, so this then, if then, x cubed is less than 0, right? So this one's a funny example because the plain English is actually easier and less writing than the symbols. But it sort of shows you where this comes in, right? And how we often don't write this symbol because it's cumbersome, but it's there sort of in the back of our head, right? This is a blanket statement that's saying, hey, if you give me a negative x, then cube it, it's also negative. Right? So that's saying for every single one that you could give me, right? It's not for a specific negative x, it is for all of them. Okay, so that's the universal quantifier. So let's talk about the existential one. So similarly, the sentence funny e of x, p of x is true. I'm going to even use this symbol to say, hey, these are equivalent. You can either one. If there is at least one x, so that p of x is true. So how many x's do I need? Who cares, right? Just one. If it's true for at least one, it could be true for exactly one. It could be true for 5. It could be true for 800 billion. Who cares, right? As long as there's at least one, then we say the statement is true. So some examples. So let's think of this. So what is this saying? It's saying, hey, can you find an x where x is bigger than or equal to squaring it? So yes or no, is this possible? I mean, we think about it and, we're used to seeing the opposite, right? Like 4 is bigger than 2, 9 is bigger than 3. So squaring usually produces a bigger result. But is that always the case? So if we do 2, then 2 squared is 4, so that doesn't work. Yeah, one works, right? So 1 is less than or equal to 1 squared, or bigger than or equal to 1 squared, so 1 works. 0 works, right? Another example, 1/2, which is 1/4 when you square it. right? So when you do something between 0 and 1, x is bigger than x squared generally, because I mean, it makes sense. You got a fraction here and you're squaring what's on the bottom of it, so you get smaller. But the point is, this doesn't matter. You gave 1. That's good enough. True, since x equals 1 works. Right? All you have to do is provide 1. Well, how about this? True or false? Oh, okay. Which numbers do you think it's true for? Yeah. Okay. Usually this one has a bunch of blank stares, but y'all have been here for a term already. You're onto my nonsense. So yeah, we could do x equals 1, y equals 1, and that would work. But the point is, you kind of look at this, and when someone says, "Hey, yeah, I only need one choice. Just find one. Just find one for me." It's like looking for a needle in a haystack sometimes, right? Because if you look at this and you're like, I just need to find one, that's not easy sometimes. Just finding one example. So sometimes that can be very, very hard. So if your instinct on looking at that is like, well, besides the fact that it's just ugly math, is just be like, that seems kind of hard to just find one. Yeah, that's true. It's funny because you look at the statement for all possible choices, and that seems like a really, really strong statement, right? So if I said, hey, prove it for all possible choices, you're like, oh, there's so many. That's really hard. But then I say, okay, well, you just have to find one then. Somehow that doesn't actually seem that much easier at the end of the day, because it's for a lot of choices it's wrong, right? But for one, it's true. I think maybe I'm wrong on this, but I think this is the unit hyperbola. Well, it won't be unit because of the 2. If you did that, it would be. But it looks something like that if you graph it on Desmos or whatever. I think. Please don't quote me on that. Don't test me. I will fail. But the point is, sometimes these are, even though we say that they seem easy to demonstrate, like, oh, I just have to find one. Sometimes that is very challenging. So where does this one come up? Generally speaking, it would come up in statements like, so this comes up. You can just leave the package there at the door. So some x that works for p of x also works for q of x. So often in like a process or an algorithm or something like that, right? Like it worked for p of x, and then so there exists some x that works for p of x that also works for q of x, right? So it works for both things, because that's not guaranteed, right? It's true for p of x. That doesn't necessarily mean it works for q. Okay, so the point here is that these kind of crop up all over the place, even though we don't write them. And it's just, the reason why it's important is for De Morgan's laws and negating statements. That's when we'll care. So let's talk about those now. So I'm going to say this: if P is some formula, not P is called the denial of P. And we're giving it a specific name for reasons I will explain in like 20 minutes. Because we want to make a distinction between this and the opposite. Because those are not the same thing. So we're giving this a name to make it distinct. So the following are De Morgan's laws. So all these do is they tell us how the negation interacts with and an or, right? It distributes almost. So this is the same thing as not P or not Q. And the similar for the other operator, not P and not Q. So let's check this with a truth table, right? Because if I'm making this claim that hey, you do have to flip the symbol there, well, okay, do you? Like, why? Well, we've got P and we've got Q. True, false, like that. And then we need to build P and Q. So that's true, F, and then we negate it. Hopefully I have enough room for this. F, T, T, T. Right, we just flip it. Okay, great. So now let's build the other piece here. Not P or not Q. Lots of people would do not P or not Q in their head. I'm going to do it here just for note-taking purposes. So we just flip this. F, T, and this is F, T, T. And now it's not P or not Q. F, T, T, T. So this thing here is the same as that thing there, which means technically there's the extra step of, well, we have this symbol. But all this is saying is if these two are the same, if this is the same as this, write down a T. So we would see same. So we'd write down T's all the way down, which is a tautology, which means we can replace this with this. They're the same thing. So we see that, okay, yes, we do have to swap the symbol, right? Because if instead we didn't, and we just wrote down, I have too many pens going. So if we instead did the naive thing and kept the symbol the same, what do we get? Not P and not Q, F, T. So that thing there is not the same thing as this, right? So we can't possibly say they're the same statement, right? They don't have the same truth tables. When this is true, the other thing is even false, right? So they're kind of opposite of each other in some ways. So okay, this was not correct, and we've now seen that through the truth table. But there's another way to think of this that isn't even in terms of math. It's in terms of just language. So consider the statement, I don't like chocolate or vanilla. So let's say I have that statement. Do I like chocolate? Do I like vanilla? Right, I don't like either. So this is I don't like chocolate or vanilla. That's the same. I don't like chocolate. And I don't like vanilla. Right, so here we have not P and Q, or sorry, not P or Q. And here we have not P and not Q, right? So just in terms of language, this makes sense, right? The way we would sort of break this statement down is it makes sense this way, right? The or becomes an and vice versa, right? An and would become an or. Okay, well, but what about a math example, right? Because it's nice to do sort of an English language example, and then we do a more mathy example. So consider x is not between 2 and 3. Okay, so it's not between 2 and 3. So now what does it mean to be between 2 and 3? Well, it means that x is bigger than 2 and x is less than 3. Right? Bigger than 2, less than 3. That's between 2 and 3. And then we say it's not between those things. So, okay, our rules, De Morgan's law, well, how do we write this in terms of symbols? Well, we move the not inside and then we flip the symbol, right? The and becomes an or. Nope. Wrong symbol. Okay, but this is something that we can think of, right? So x is not bigger than 2, which means it's less than or equal to 2, right? We flip this symbol, right? X is less than or equal to 2, because if x is not bigger than 2, then the sort of opposite of that is less than or equal to 2. Same thing here. X is less than 3. We're actually saying x is not less than 3, which means it's x is bigger than or equal to 3. Okay, so what is this saying in words, though? This is saying x is smaller than 2 or bigger than 3. So right, in terms of just language, x is not between 2 and 3. Right, so that means it's something outside of that range, right? It's not between 2 and 3. So that means it's smaller than 2 or it's bigger than 3, right? Or equal to, because we do have that symbol there. Okay, so we can see how this sort of works with language. So this is how it interacts with this and or, but this law also interacts with those quantifiers. And this is sort of an important part of logic that is a bit, I don't want to say it's hard, but it's easy to make these mistakes. These also interact with quantifiers. And sort of in the same way. So if we have not for all x, p of x, what it does is it flips the symbol, right? For all becomes there exists. And then we put the negation in front of the p. Same thing here. There exists an x. The exists becomes for all. Like that. So this one, we can't really understand it from truth tables because, I mean, this is either true, in which case, well, this should be true too, or it's false and that should be false. That doesn't really help us very much. So let's just think about examples in terms of language. So suppose X is from the set of cars. So it's just a car. It's your car, or if you have a weird car, it's someone else's car. So let's consider if P of X is X has four-wheel drive, then the denial, so that's why I defined that, it's the, the negation of it, of every car has four-wheel drive. So this right here is so we're forming the not of this thing. That's what we want to do, because this is for all x, P of X. So if I said every car has four-wheel drive, let's say that was my argument to you. I was saying, yeah, every car has four-wheel drive. How would you prove me wrong? What would you say to that? How would you prove that statement wrong? So I'm claiming every car ever has four-wheel drive. So what's the easiest way to disprove that? Not the opposite. So think, yeah, exactly, right? Does your car have four-wheel drive, or do you have a truck?
No.
Okay, so that doesn't have four-wheel drive. Then you already are like, well, mine doesn't. So I just said every car has four-wheel drive, and your response is no, that's not the case. Mine doesn't, right? And that's good enough to sort of counter my argument of saying every car has four-wheel drive. You're just like, no, that can't be the case. Mine doesn't, right? So the denial of that is there exists, or there is, a car that does not have four-wheel drive. Right, so we think, okay, I said every car has four-wheel drive. You want to sort of deny that. You want to form the denial of that. So you just say there is a car that does not have four-wheel drive. So that is, there exists a car such that it does not have four-wheel drive. Right, so we can kind of see how we've swapped the symbols, right? This went from every car, and then when you put that not in front of it, this is what we get. I mean, the more natural English way of saying that is not every car has four-wheel drive, but for the purposes of understanding these symbols, we're gonna word it that weirder way. So another example is X has three wheels. Then the denial of there exists a car with three wheels So I'm saying, hey, there's a car with three wheels. Let's say that's what I'm claiming. And you want to say, no, that's not true. What would you need to present to say that's not true? I'm saying, hey, there is one. Just in terms of language, don't worry about math. I said this to you. I came up to you and said, hey, there's a car with three wheels. And you want to say, no, that's not true. What would you offer to counter that?
That every car has four wheels.
That's how we would say it naturally, yeah. But that's equivalent to saying there are no cars with three wheels, right? Or that every car does not have three wheels is how I would phrase it in terms of these symbols. But that's exactly right. If I said, hey, there's a car with three wheels, you'd be like, no, every car has four wheels, buddy. And I'd be like, well, my piece of shit only has 3 wheels, so whatever. But the point is, if we want to deny this statement, it's a couple ways of putting it. Every car does not have 3 wheels, just to match the symbols. So in this case, up here, this is, there exists an x, e of x. And then we're saying, hey, put the not in front. This is that, right? So the point here, the reason why we're saying denial is to sort of draw a distinction between denial and opposite, because they're not the same thing. So if I said all people are tall, how would you disprove me, right? If I said all people are tall, what's the counter argument to that? Yeah, right, exactly. There, well, so hold on. No, because that's the opposite. So if I said every person is tall, and you're saying, this is English language stuff now. I think you're saying the right thing. It's just English stuff. You're ultimately saying that there is someone who isn't tall, right? Yeah. So that's if I said all people are tall, and you said no, there's someone who isn't tall, like I'm not that tall. I'm like average, right? So you just say Travis is average height. He's not that tall, and that would be good enough. And that's a distinction between the opposite, which is if I said all people are tall, the opposite of that is no people are tall, which is also the same thing, but opposite, right? So if you're, this is like high school debate club stuff. If you've ever like walked by in your high school or whatever, or in university, and you just hear like a bunch of people arguing back and forth, I would say like 9 times out of 10 in that debate club, the reason why they're doing that is because they're doing that. They're just saying the opposite. So someone says, all people are tall, and then the person's like, no people are tall. And it's like, what are you doing? You're just going to go back and forth. Like, you're both basically making the same claim. You need the same amount of evidence. So if someone said, all cars have 4-wheel drive, and then you said, hey, no cars have 4-wheel drive, then actually you're the ass, because then all that person has to say is, well, I just claimed that every car has 4-wheel drive, which means I know of at least one that does. And you just said no cars have 4-wheel drive. So there's one that does. So what do you have to say to that? And then you're like, oh, well. So this is just, it's a logic thing, right? And it's not going to come up that much. In terms of math, it's an important distinction to know the difference between the opposite and the so-called denial when you're doing a proof, because you don't want to accidentally make a stronger claim than you mean to. So, if I said X has, like, all cars have 4-wheel drive, and you want to say no, that's not true, you don't want to say no cars have 4-wheel drive. You just have to say, hey, I know of one that doesn't, and that's good. Like, the onus is on you, man. You've said all cars have 4-wheel drive. You need to explain why, because I just found one that doesn't. That seems like a strong thing, and that's true in math, right? So in math we're arguing. I mean, there's no. It's all numbers and stuff like that, right? But if I'm claiming, hey, this is true for all numbers, right? All possible numbers, and you just say, well, wait, that one doesn't work, then it's like, why did you think it was true for all numbers? What's your reasoning for that? Like, how did you arrive at that conclusion? So that's the distinction, right? If I said it's true for all numbers, your response wouldn't be it's true for no numbers. I'd be like, oh yeah, which ones doesn't it work for? And then you'd be like, I don't know. So it's just important for proofs. Which kind of, this whole thing lets me sort of lead into talking about quiz 1, which was the quiz I gave you that made you feel bad about your math skills potentially. Which, again, you don't have to, because it was exactly what I expected. Which in your head might be like, oh, does that mean I'm bad at math? No, you're not. It means it's probably been a really long time since you've done math, is most likely. So when I asked, hey, factor these quadratics, most people were like, I don't remember how to do that. And I'm like, good, because I kind of hope you didn't. Because if you did, then that means you are probably at least somewhat experienced in maybe calculus. And then some of the things I'm going to talk about, you're going to be like, whatever. But the fact that everyone was like, I don't remember how to do that. Another one was I said, hey, do long division. Like most people are like, what? I haven't done that since like, because when do we teach that? Like if we even teach it anymore, I don't even know if we still do, because I'm 36 and maybe primary school has changed in 30 years. But I remember doing it like fourth grade, maybe sixth grade. I don't know. But like long division, it's been a long time since you've done that. So most people either didn't remember or they went and looked it up so that they could remember how to do it. So there were a couple things there that no surprises. Same thing with the last question, which was, solve these systems of equations. Most people were like able to like poke and prod and play around with it a bit, maybe do like the high school method if they remembered, or they just wrote, I don't know. That's fine. We're going to talk about that a lot. But the reason why I'm talking about it is there are pieces of advice I can give for math that are quite helpful. And it's going to sound silly when I write it, but it's just try numbers. And so this is a funny lesson that many of my colleagues in math, who are pure mathematicians, have struggle with. Because if they're presented with something and they're like, is this true or not? They just immediately go to abstraction, right? And they're trying to prove some like abstract statements. And it's like, what are you doing? Just try some numbers out, right? Like, to me, this is sort of the programming approach, right? You've got an unknown function. You don't know what it does, but you know what you can plug into it. You know what the inputs are. So how do you figure out what it does? You plug in some inputs, right? Just plug stuff in, see what happens. Print it to the console, see what comes out. Oh, that's what came out for that input. Oh, that's what came out for that input. And then you're like, I think this is what it does, right? So just try some numbers. So in math, if you're like, is this true or not? Try some numbers. So an example is, this was in the quiz. Is it true that so we had this. Now this is kind of what I mean with math, is that those universal quantifiers and stuff, they're always there. We just don't write them. So what this is actually saying is it's a formula. So we're claiming it's true no matter what you pick, right? Any choice of X, A, or B, should this be true? Now, when you're faced with a formula and the question is it true or not, you should just try things, right? Just plug in some numbers and see what happens, right? So in this case, what happens if I do A equals 1, B equals 2, X equals 3? What do I get? Well, left-hand side is 1 plus 3 over 2 plus 3. Okay, that's 4 over 5. All right, that's some fraction, whatever. Right-hand side, what do we get? 1 over 2. Is 1 over 2 the same number as 4 over 5? No. So that means, because of this, again, we don't write it down, but for any formula in math, we're kind of assuming that is written, because what is the point of a formula if it's not true for every possible choice, right? If it's just true for some of them, then it's not a formula anymore. So the point is, it doesn't work for these numbers, which means this is a false statement. We need more. Now, that doesn't mean it's false for all possible choices. It just means, hey, I found one where it's not true, and Travis, you were saying that it's true all the time, no matter what I pick. And I just found a situation where it didn't work, so you lied to me, right? Is basically what that would be saying. So when you're trying to check something, just trying some numbers can be very, very helpful. Let's say in this example, we tried these numbers and it worked, right? Okay, maybe we got lucky though, right? there's no guarantee that just because it worked once, it's going to work every time, right? Like, we chose 3 numbers. There are infinity numbers. There's a lot of numbers. So, got to try more. So let's say this is a mistake that I see. Well, mistake. Some students will just go, okay, 2, 3, 4, right? But, and again, this is it's you've already taken Python, so you already know debugging and stuff like that. But 2, 3, 4 is a bad choice because we just did 1, 2, 3, which is 3 sequential numbers. 2, 3, 4 is also sequential numbers, so maybe it just works for sequential numbers. So what I would do is I would be like, okay, -3, 4, and 8, or something, right? Or 7 or something, just like totally random numbers. Now I got a negative number in there. Does it still work? Okay, cool. Then after that, I'd be like, oh, still, okay, that worked too. Still, that's good evidence. It doesn't mean it's true, just good evidence. And then I'd be like, well, I'm going to try a fraction now. And you just try different inputs. And again, trying this, like testing yourself to see if something might be true in math is very much like building unit tests, right? Like, what random crap can I try in there to see if it works? Like, if this were programming, after trying those, I'd be like, all right, I'm going to try A equals aardvark. Like, is that a valid input? No, but I mean, someone's still going to probably try it, so I better make sure that it doesn't explode. But, again, in math, like, we're limited to numbers, but like the same idea is still true, right? Just try different numbers. And let's say it worked for like 3 or 4 and you weren't doing like sequential numbers every time. You did like random stuff. And let's say it worked for all 3 of them. And you're like, hey, okay, there's probably something to this, right? There is a reason why this is working, right? And the reason why I'm saying this is you want to try multiple times is because you might get lucky. So in this example, let's try A equals 1, B equals 2, X equals 0. What do we get? Well, our left-hand side is 1 plus 0 over 2 plus 0, which is 1/2. So our right-hand side, it's 1 over 2. Oh, those are the same, right? So, but we saw, if we tried different numbers, it didn't work. So again, the claim that it's true for all possible choices can't be true because we found one where it doesn't work, but it works for some of them. But that's not the point. The point is for a formula, we're saying it's true for all possible choices. So, because like here's another formula that you've probably seen, and don't worry about it. Again, I'm not going to emphasize trig, but there are a lot of formulas for trig. So this one here. Does anyone remember what that is? This identity?
No.
Hey, 1. Yep. So again, it's because that's a terrible circle, but it's sine and cos are the coordinates on this unit circle, and that's length 1, so that's why it's 1. But anyway, the point is we're not worried about trig. The point is we're worrying about this is saying it's true for all possible choices, right? That's why this formula is valuable. That's why it works, because anytime you see this, sine squared plus cos squared, no matter what that theta is, it's 1, right? Because it's true for all possible choices. So if it were true for only like some of them, then it's just not useful, right? It's just not a useful formula. If I was like, well, it's true for like 3 and 5, you'd be like, it's not a formula. That's just a random factoid, right? So these quantifiers here are always present for formulas because that's what makes them useful, is that they're true all the time, or true under the given situations, right? Like it might say like theta bigger than 0, but that means still for all possible choices bigger than 0, it's true. So yeah, if I plug in a negative number, it's not going to work anymore, maybe, but that's not valid input anyway. It's saying, hey, it has to be bigger than 0 for this formula to be true. So therefore it's true for all of those. So yeah, again, the point here is that this is ever present, but we don't write that, right? We just write down the formulas. So that's kind of my point, is just it's true all the time, which means if you're not sure, just try stuff. Just plug in numbers, right? Ultimately, all there is. And the reason why this is helpful too, thinking about this negation stuff, is I'm thinking in terms of, well, let's go back to the car example. Because there's a lot of times where you'll reason this way in mathematics. I said all cars have four-wheel drive. Well, if I think about the denial of that, it can lead me interesting places too. Because let's say I just didn't know. That was my claim. I was like, hey, I think all cars have four-wheel drive. Well, if I thought about the counter argument to that, it's there is a car that doesn't have four-wheel drive. I'd be like, huh, is there? Let me start thinking about that. Let me start thinking of examples of cars that I know. And I'd be like, oh, there's one that doesn't have four-wheel drive. Oh, okay, well then that means my statement is wrong. So in math, that's interesting to us, right? Because we're not. It's sort of built on very concrete rules, right? That adage of like there's only one right answer for math, which is bullshit. That's not true. There are sometimes multiple ways to get to the same answer. But the point is, we're used to that, right? We're building up like that. So if we start thinking about, okay, let's sort of suppose I'm wrong, right? Like if I'm making this claim, what would happen if this weren't the case, or what's sort of the counter argument to this? It can lead you to thinking of situations where it may or may not be true. So like, you know, AB is equal to B times A. I'm saying this. You could swap the order from them. These are matrices now. The denial of this is, hey, there's an A and B where they're not equal when you swap them. And I'd be like, huh, interesting. Okay, let me start thinking about that. I'm starting to poke and prod at examples where it's not the case, right? And then you end up finding one pretty quickly that it's not the case. And you're like, oh, well, I guess what I wrote down was incorrect. So it's just helpful for reasoning your way through things in math. You're not going to do a lot of math proofs, so don't worry too much about it. But we'll use like techniques like that to argue in this class. So it's kind of just important to think about that. Okay, well, that's all I have. So next class, we're just going to basically do a bunch of Boolean algebra. So I'm just going to do a bunch of examples of like simplifying logical expressions and that sort of stuff. And then maybe we'll start with a truth table and then end with a truth table, and we can see that they're the same, and we're like, hey, we did it right. That sort of stuff. And then it will just be a quiz, which will just be basically what we're going to do on Wednesday. It's going to be just, we're going to do a bunch of examples like that, and then I'll be like, all right, here's the quiz. It's what we just did, basically. So, yeah. And I gave you 8 minutes back on Monday at 7, so that's pretty nice. No, sorry, that's on Wednesday.